Good evening and welcome to the first of two videos on section 12.3 in your textbook, which is limits and an introduction to calculus. But section 12.3 is all about what we call the tangent line problem. Now, this, above all, is going to tie together the difference quotient that we've been talking about way back since chapter 1, along with some of the limit notation that we talked about in the previous two sections in chapter 12. This, it really is the first introduction that you'll have to the calculus. And so pay very close attention as we go through this section, because you're going to see things that you've seen before, but we're going to tie them together in a slightly different way than we have before. All right. So the tangent line problem is essentially this. All right. We start out by talking about what the whole point of calculus is. All right. And the entire point of calculus is to examine the rates of change of functions. All right. Now, generally speaking, if you're talking about a straight line function, this is a very easy thing to calculate, all right? Because all that the rate of change is the slope of that line. And it could be positive, it could be negative, it could even be zero. And so, but that slope is the rate at which the function is changing as it goes, as the value of x changes. So, the slope of a line, a straight line, indicates the rate at which a line rises or falls, right? Because it could be positive or negative. For a line, this rate is the same at every point. In other words, no matter where on a line you measure the slope, you're going to come up with the same number, all right? The slope of a line is constant. It doesn't change. However, for graphs other than lines, the rate at which the graph rises or falls changes from point to point, right? If you're looking at a curve or a parabola or anything else that's not a perfectly straight line, then if you measure the slope at two different points, you're going to get two different answers, right? And this presents a problem. However, Sir Isaac Newton invented the calculus in order to get around this problem. And it actually will allow us to calculate the slope of a graph at a given point. So, to determine the rate at which a graph rises or falls, you can find the slope of what we call the tangent line at that point. And I'll show you what that means in just a second. But the word definition here is that the tangent line best approximates the slope of a graph at a given point. Now, what does that mean in plain English? All right, well, what it means is that if you actually look at a curve and you're trying to calculate the slope of the curve at a given point, you draw a line tangent to the curve. Now, what is a line tangent to the curve, you ask? Well, the word tangent means that it touches the curve at just one point. That point, the point that we're talking about here. So let me give you an example. All right. Actually, I'll give you 5 examples. All right. In this particular diagram, you've got this funky looking sinusoidal curve. It's not actually a sine curve, but it's similar in nature because there's rises and falls here. And you can see that in certain sections here, all right, for example, this section along this area, we've got a positive slope. We're increasing and increasing. And if I tried to calculate the slope at this point right here, the red line, this red line represents the slope. That is the tangent line. The tangent line on this side is here. And of course, this tangent line has a negative slope. This tangent line, interestingly enough, is parallel to the first one, or actually, well, the second one, and it also is negative. This tangent line, to me, looks parallel to the first one, and it's positive again, and so on. But in all 5 cases here, notice that the line, the tangent line, only touches the curve at one point. And so it's tangent to the curve at that point. Okay. So this allows us to then think about what the slope of a graph, especially a curved graph, is at any given point. Because the tangent approximates the slope of a graph at a point, the problem of finding the slope of a graph at a point is simply the same as finding the slope of the tangent line at that point. Okay? So in other words, if I want to go back here and if I want to go back here and figure out what the slope of the curve is at this point, all I have to do is calculate the slope of this tangent line. If I want to find the slope of the curve at this point, all I need to do is find the slope of this tangent line, or this tangent line, or this tangent line, and so on. Okay? So again, because a tangent approximates the slope of a graph at a given point, the problem of finding the slope of the graph at that point is the same as finding the slope of the tangent line at that point. Okay, so let's start with a couple of examples, and hopefully this will begin to make a little bit more sense as we go through. So, example number 1. It says use the figure, and I'll pop the figure up in the next slide, so just give me a second here. But use the figure to approximate the slope of the graph of f of x equals x squared at the point 1, 1. All right, so let's think about this. We know that the graph of f of x equals x squared is a parabola. All right, so big old U shape, all right, with the open side of the U facing upward. What we want to do in this case is find the slope of that graph at the point 1, 1. Okay, so how do we go about this? Well, first and foremost, let's actually draw that graph. Now, I've used Graph Sketch to sketch this graph. This is the function f of x equals x squared. And what I'm interested in doing here is finding the slope at this point. All right, that point is 1, 1. I didn't do a very good job of drawing a point. Now, the tangent line is going to run, and this is not going to be very pretty, but right here, and it's going to look something like this. All right. And that's sloppy, and I promise in the next slide I'll actually have drawn it in using Graph Sketch, and so it'll be a little bit prettier. But if I can now calculate the slope of this red line that I just drew here, then that will give me the slope of f of x equals x squared at the point 1, 1. All right, so here's the actual line drawn in by the computer rather than me trying to draw it freehand by the mouse. Now, if you look at this line, you should, right off the bat, be able to tell that it's got a slope of 2. All right, how do I know that? Well, I can do this in a couple of different ways, but the easiest way is to, let's do green ink. All right, I'm going to choose 2 points. This point and let's say this point, okay? And remember that the slope of a line is equal to delta y over delta x, all right? Well, this point here is 2, 3, and this point here is 0, -1. And so in this case, delta y is going to be 3 minus -1 all over. Delta x is going to be 2 minus 0. Oopsie daisy. 2 minus 0. And so that's going to give me 4 over 2, or 2. And so I know right off the bat now that the slope of the tangent line is 2. All right? Everybody follow that? That is the way that we calculate the slope of a graph at a given point. Okay, the given point here is this point, all right, which is 1, 1. All right, but in order to calculate the slope there, I draw a tangent line that passes through 1, comma 1, but doesn't touch the graph at any other point. And then I calculate the slope of that line. And the slope of that line in this case is 2. Okay. Now, how does this relate to limits? All right, in sections 12.1 and 12.2, we went through the idea of how to actually calculate the limit of a function. So the reason that we did that is because a more precise method of approximating tangent lines is to draw a secant line through the point of tangency and a second point somewhere on the graph. Now, this is where it gets a little funky, okay? And the notation gets a little ugly. So the point of tangency is going to be x, comma f of x, all right? The x and y values here. However, what I'm going to do is find another point on the curve, all right, a secant line, and I'm going to show you this picture again in the next slide, just a little bit bigger. But what I'm going to do is I'm going to add a value h to the value of x, all right, and so I'm going to expand the horizontal axis by an amount we call h. All right, and what that's going to do is it's going to form a secant that passes through the curve twice, not once like the tangent, but twice. If you look carefully at the diagram, the red line there is tangent to the curve, right, and it passes through the point x f of x. And then there's a green dotted line, which is the secant. It also passes through x, comma f of x, but it passes at a second point on the curve at x plus h, comma f of x plus h. Okay, and so these are the 2 points: x f of x and x plus h f of x plus h. Now, if I go to calculate the value of the slope of the secant, again, that's going to be change in y over change in x, delta y over delta x. Well, the value of the second value of y is f of x plus h. The first value of y is f of x, and the change in the value of x is this little teeny sliver of horizontal axis that I'm going to refer to as h. Okay. Now, if you look at this, does it look familiar to you? It should, because this is the formula for the difference quotient. Okay, and we talked about this in section 12.1 and 12.2, as well as in chapter 1. All right, so the right side of this equation is called the difference quotient, and it gives us really the slope of a secant line for our curve. And interestingly enough, this is also f of x equals x squared. Now, here it is again, a picture of this blown up a little bit so that you can see it a little bit more clearly. Notice the red line is the tangent line, and it passes through or touches the curve only at this point right here, x f of x, okay? But I chose a second point on the curve, which I'm going to call x plus h, because if this is the value of x, this is the value x plus h, all right? And so the difference here between these two is h. And so this is the point h plus x, or x plus h rather, comma, f of x plus h. Now, if I calculate the slope of this green dotted line, which passes through both points here, I get the slope of the secant. And that is the difference quotient. Now, here's the real rub. If I take the limit of that difference quotient, or the slope of the secant, As h approaches 0, so the value of h is getting smaller and smaller and smaller and smaller, really, really close to 0, then I get the slope of the tangent. Okay, so the limit as h approaches 0 of the slope of the secant, which is the difference quotient, is equal to the slope of the tangent. All right, let that sink in a little bit, because that's an important aspect of this. Okay, so the definition of the slope of a graph. The slope, and we're going to go right back to using the notation that you used in high school, m. All right, the slope m of the graph of f, a function, at the point x comma f of x is equal to the slope of the tangent line at x comma f of x. And it's given by m equals the limit as h approaches 0 of the slope of the secant line. And of course, the slope of the secant line is f of x plus h minus f of x all over h. And as long as this limit exists, in other words, it approaches the same value from both the left and the right, then the slope of the secant, the limit of the slope of the secant as h approaches 0 is the slope of the tangent line. Okay. Now, that's an awful lot of information I've just given you there. All right. You might need to go back and look through your notes again. Make sure that you're following all the things that I'm saying. All right. We started with the tangent line. Then we went to the secant. All right. And we know that the limit of the secant line as h approaches 0 is equal to the slope of the tangent line, as long as the limit exists. Okay, so let's look at another example then. Okay, we're going to use the same graph, all right, f of x equals x squared, but this time we're going to try to find the slope of the graph at the point -2 comma 4. Okay, and we're going to do this by using the slope of the secant, or in other words, the difference quotient here. All right, so find the slope of the graph of f of x equals x squared at the point -2 comma 4. All right, so here the blue curve obviously represents f of x equals x squared. And the point -2, here's -2, 4 is right here. Okay. And so I want to calculate the slope of this line. Now, because I've got a very pretty graph right here, if you look at this very carefully, all right, you should be able to figure out that the slope of this line is -4, right? If the y value here is 4, the y value here is 0, so 4 minus 0 is 4, and then this is -2, and this is -1. So -2 minus -1 is -1. 4 over -1 is -4. So the slope of the red line, the tangent line, in this particular picture is -4. However, I want you to actually do this or calculate this using the difference quotient. All right, so let's say that my slope here is going to equal the difference quotient. So it's going to be equal to f of -2 plus h minus f of -2 all over h. Okay. Now, since f of x is equal to x squared, the slope is going to be negative, whoops, let me put a parentheses there, 2 plus h quantity squared minus -2 quantity squared over h. All right. Now, if I do the FOIL method, negative 2 times negative 2 is 4. Negative 2 times h is negative 2h. Negative 2 times h is negative 2h, so that's going to give me negative 4h altogether. And then h times h is h squared. Okay, and so that's my first term, minus, now, negative 2 squared is 4. Okay, all over h. Now, go right through this. The 4 and minus 4 cancel out. I'm left with negative 4h plus h squared all over h. And so that's, if I cancel out the h's, the value of my slope is going to be negative 4 plus 8 h. Okay? Now, I need to take the limit as h approaches 0 of, come on now, of negative 4 plus h. Well, if I just use the direct substitution method, h becomes 0, and so this equals negative 4. And so there is my slope, all right? So that is the slope of the graph f of x equals x squared at the point negative 2 comma 4. All right, the slope is negative 4. Now, just looking at the graph, we knew that, but the difference quotient actually proves it. Okay, so that brings me to the end of the first of 2 videos on section 12.3, and I hope you learned something.